So we were in the middle of this decay of matrix coefficients or mixing, from which we only care about ergodicity, but let me remind how the proof went. Okay, and what are a couple of separate statements. So on one hand we had Mautner, okay, I think this n is not there, which says that G naught we have this unitary representation with the continuity properties, and we have a sequence of guys which do this business, which you always need to have in mind that this is diagonal or hyperbolic dynamics, and H is some sort of stable or unstable direction when you see this type of thing. And ANX goes weakly to C, then HC equals to C. So this is a excellent way, ultimate way of finding invariant vectors for the guy. And in a way, from a purely dynamical point of view, we think of this as the fact that Birkhoff averages are constant along unstable or stable directions. Even though this is stronger than this fact, but it's very much on this line. The second theorem is so we state it in 2 steps. I'm going to state it only 1 step, and then I will improve it. So it says that if I have now a unitary representation of SL to R, and I have an invariant vector, then this is invariant for everybody. Okay, and then using these 2 things, well, before that, I will upgrade this theorem to the following theorem. Yes. Okay, I mess up, but I think I mess up. Let me give me 1 second. Okay, that's not what I wanted. Okay, whatever. I will just state it, and when we see how we prove it. Okay, so I have now a unitary representation again. Let me just add, as always, continuous. So what does it mean to be continuous? We already discussed it, so it's always in the same sense of SLR, and it's essentially the same as before, but now I take, so here H was these matrices, Actually, maybe I should have put T in R. And now I will have similar HT. Let me call it HS. Is this math which has all ones here and an S in the ij position. Ji position. And assume H ij S of Z equals to Z for every S T. For one ij, any of them, then G of Z equals to Z for every G. So then G, this is invariant. Okay, so that's one thing we are going to prove today. It's actually followed from playing with the previous one, with the previous discussion. Wait a second. No, that's not what I want. That's not. I want something else, something more, which I will have, such that this is true for every T and for every J for some. So let me and assume there exists J. I'm sorry. It will be the same, but such that J naught. But this is true for every T and for every I. Okay, now it's better. And S is the same as T. Yes. Thanks. Yeah, so I want all the column guys to have this invariant. Of course, I different from J naught. For J naught, it should be identity, and we are not putting for J naught. So, but I have all these guys, then it's an invariant vector. Okay, now it is better, the statement.
So do you need invariance along the whole column entries or just?
Yes, along all the columns. So for every, I fix the J node and it have to be for every I and for every S. So all the column entries, I need to have invariant.
Not just of the triangle.
No, just, well, yeah, not just of the triangle, even though in the argument I will just make some change of coordinates and I will put them all the way at the end. But it really doesn't matter. We will see in the argument what's really, why we care and how we do it. Okay, let's prove the theorem. Okay, now before I prove the theorem, let me just finish the Howe-Moore theorem with this. So Howe-Moore. So remember we start with Gn, and we assume this is larger than epsilon for every n. We wrote Gn as Kn times An times Kn prime. We took subsequences and we assumed that Kn prime, Kn goes to K, Kn prime goes to K prime, and by moving to epsilon over 2, we could assume that An B bar dot W bar is larger than epsilon over 2, actually the same epsilon for every n modulo taking subsequences. and actually B bar is essentially K of B and K prime of B, and W bar is K inverse of W. So they have the same norm as B and W. It's not that it's important, but okay, now we take a subsequence. So A, N are diagonals. We take a subsequence. This is e to the Tn1. Okay, and I repeating the same mistake. I hope you don't complain too much. Tnn, but one n is going to infinity and the other n is dimension, we never moves. So we have to do it. Now we are good. T1k, tk. And then I have k sub k, yes. But one is, you don't notice, but this is kappa sub k. Oh boy. Okay. And sometimes I cannot even distinguish between my k's and my n's. So anyway, I'm sorry. Okay, so we have this a sub k's. And again, by taking subsequences, we can assume that t, and there comes the j naught essentially, should be, I hope I'm making the right choice, minus t j naught plus 1k goes to plus infinity. Okay? Or to minus infinity. Let's say in absolute value, just to make. Okay, since the sum of all of them is 0, and I know that Gn goes to infinity, which implies that the norm of Gn goes to infinity, k and k prime has norm 1, so the norm of ak goes to infinity, and the norm of ak, whatever norm you chase, is comparable to this e to the t thingies, and since the sum is 0, I need to have this difference going to infinity. Because if not, all the difference will be bounded, the sum is 0, each individual guy will have to be bounded. Now, I will do the computations to check what I need to choose, but either I want this to go to plus infinity or to minus infinity, and if it's going to plus infinity and I need it to go to minus infinity or vice versa, I can switch this guy I don't make any choice. No, it's okay. If it goes to plus infinity, I do one choice, and if it goes to minus infinity, I will do a different choice. We are going to discuss it in a second. Okay, so now is one time where, by just making some change of variable or conjugation in the group, I can assume that J naught is just the last column. Okay? This difference is happening in the last two entries. I could choose the first two, or I could just go in the middle. It really doesn't matter. It's just for the picture and for what comes at the very end of the argument. This is without plus 1. Tn minus 1 up to n. Okay. So I want to find my h, which to apply Mautner with respect to this sequence of ak's. So I do ak inverse times hij times ak. And ijs, and I want this to go to identity. And this will be true for some choices of ij. And I'm going to look what are the choices of ij, and it will be exactly the ones coming from the last theorem if I do things correctly. So I conjugate now by this ak, this matrix. So I have 1, 1, 1, I have the S in the ij position, and then I conjugate. And when I conjugate, what I get is that this S becomes e to the tj minus ti or ti minus tj. And we will see whether we have an S, a plus or a minus. We discussed this last time. Let's discuss it again. So I have e to the minus t here and e to the t here. So when I multiply this I with the I is positive, and this goes with the j. Is it correct what I'm saying? Because, yeah. So this is the I line. Oh, but this in the j, when I multiply it with the j position, is where I got the S multiplied by e to the tij. Yes. So it's a minus here. Okay, good. One should do it carefully at home, but okay. Anyway, so that's what you get. And so what I want to choose is the ij's such that tijk minus tjk goes to to plus infinity. Because as soon as I take these guys, this goes to 0, and then this goes to identity by this choice. Okay. Now I need to maybe do a better choice than what I discussed here, because this only gives me one guy. Although I could apply Mautner and then this and then that. That could be, yeah, that's yeah, let's do that. Okay, so we assume this goes to plus or minus infinity. So if I want this, let's say tn minus 1 k minus tn k goes to minus infinity. If it goes to plus infinity, we do pretty much the same. So then we take I equals to n, j equals to n minus 1. And by this choice of I and j, I go that this goes to plus infinity, and hence Mautner tells me that h n and n minus 1 is of any weak limit of akb bar, which is c, is equals to c, where I am assuming ak of b bar goes weakly to z. And I want to show that c is 0, because once c is 0, then this product is going to 0, contradicting the epsilon. So, or if you want, since we are in the middle of the contradiction assumption, c cannot be 0. Okay, now this implies by, maybe I should put a number here, 1 and 2. This implies by theorem 1 that z is also invariant by the following matrices. So let's position this guy. So this is n minus 1. So, and everything else is 0. Still, I want to remark this guy. So this is h n minus 1 s. And once I have C's, I have this SL2R appearing here times identity. I restrict my attention to this SL2R times identity, and the theorem 1 tells me that then is invariant by this SL2R. Okay, so I get Z is invariant by this SL2R. Now I need to show invariance by all the others. And then actually, yeah, I think I need only I naught, J naught. We will see in a second for the next argument. So I only will need one I naught, J naught in the second theorem, but I will redo the argument in the proof of the theorem with I naught, J naught, the same as the argument we are going to discuss here. Okay, so I have invariance of Z by this SL2R here, and now I will show full invariance. And to show full invariance, I will again use Mautner and again use theorem 1. So let me repeat here the picture. I have GZ equals to C for every such G here. Here I have identity. And now, in particular, I have that these guys times Z equals to Z. And now I apply Mautner again for this sequence A sub t, or for the subsequence of the A sub t's, if you want. We call this A sub t or D sub t, whatever. And for this D sub t, I do the same computation as before, and I want to know which are the H which goes to identity, and then I can check that when I do H dt, and when I do the ij, what I get is the same as before, h e to the ti minus tj times s. Okay? But now this e to the ti minus tj here is all zeros unless I get the last two entries. So I get that if let's say j equals to the last one, n, and I is different from n, anything different from n, then what I get is actually different from n, and I is different from n minus 1. Then I get the ti is 0, and I get that this guy is h I n e to the, oops, I forgot the minus here. And then I get minus tn, which is t, times s. Now, I have this equality here, so if I take any subsequence dtk of c going to whatever limit, it will have to be c because it's always c. I take then tk going to minus infinity here, and I get that z is invariant by all these guys, by Mautner. Hs in s of c equals to c for every I different from n, I different from n minus 1. So I win invariant by all these elements now. All this column. And this entry I already had, so I don't need to care about this entry. I could do it again for this entry, because if I take now n minus 1 n, then I have minus 2t, or I have 2t here. And again, I send t to the minus infinity, and I'm done. So I got invariant for all these guys. By the very same token, if I wish, I don't need it. you will get invariance by all these horizontal. Now, what is important here is not that. What is important is whenever I take this guy here, let's say this is the IN, then I have the NI, the NN, and the II entry. And when I put these four entries together, and all zeros or ones in the rest, I have a copy of SL2R, which is the copy SIN of SL2R, which correspond to all these. And now, I again apply Mautner, and whenever I have this entry, then I have the four corresponding entries. Okay. So, essentially, this should do it. Now, by using this argument, essentially, I apply. Well, I don't even need to apply induction. So I got invariance by all the diagonal elements because all these guys I wrote generate the diagonal. So the diagonal is generated by e to the t, e to the minus t in the I, j position. If you put these guys, you generate the diagonal. And then again, I use Mautner. And once I have invariance by the whole diagonal, then I will have invariance by the whole upper triangular by Mautner and by the whole down triangular, and then I'm done. Okay, so this shows that C is fully invariant, and the main hypothesis in Howe-Moore is that there are no invariant vectors. And then Z has to be 0, a contradiction because C was not 0. Okay, so that's the proof of Howe-Moore. Now let me show how this same argument is proved in theorem 2. So let me redo what we discussed here, and let me do the improved theorem 2. For some reason I doubted, but I was right. So we just need to assume invariant for one guy, and then it will be full invariant. And the proof is the same as what we did. Okay, so you have this C. So we have this I naught G naught entry, and we have invariance along this direction. Okay, now as before, without loss of generality, I can bring this direction here, and again, this is just for doing the picture more clear. I restrict here, I earn invariance by all these just by the SL2R version of the theorem. Then I use Mautner, and I get invariance by all these guys, and the corresponding diagonal guys. But the corresponding diagonal guys generate the whole diagonal, so I get invariance by all this. And then we just use again Mautner, and once I have invariance by the diagonal, I get invariance by all the guys above and by all the guys below, and then I get full invariance. And that's the proof of theorem 2. That gives a Howe-Moore, which the importance for us of Howe-Moore is about ergodicity. Is that every element acts ergodically. If one acts ergodically, or the whole action acts ergodically, then every element acts ergodically. So the corollary, well, every non-compact element. So says that if I have the standard G action on G mod gamma, gamma a lattice. Actually, you don't need it to be a lattice, but if it is not a lattice, I have less numbers there. Then the G action on G mod gamma is ergodic. That's almost trivial because it's transitive, it's fully transitive in the group sense. I'm taking Haar measure there to consider this. And then this induces the representation pi in L2 G mod gamma. I remove the constants, so the sub-zero means integral 0. I remove the constants to make sure there are no invariant vectors. And then I get that every G in G such that not belonging to a compact group is acts ergodically and even mixing. Okay, in particular, this is one very simple proof after you prove Howe-Moore that the recycle flow on SL2R mod gamma is ergodic. Okay, that the geodesic flow, of course, but also, and not only ergodic, that it is mixing. Okay.
Playing with the same arguments, you can even show higher mixing.
Okay, yeah, that would be nice. You have, of course, to do something because then, so yeah, you can induce and do some tensor and make it, so you want to write the multiple mixing as standard mixing, but in a larger space. Because here, so to discuss higher mixing, you need really to look at L infinity functions, because at L2 functions you may lose integrability. So you really want to be able to write the correlation. And so you are essentially triple mixing will correspond to this property. Then you put the x, the x, and you are sending G1, G2, and G3 to infinity, and all functions phi, actually it's the same phi, has 0 average, or you can put phi 1, phi 2, phi 3, but they have 0 average, and you want this to go to 0. And as always, you can use the invariance and forget about the last gun, and you are just assuming that G1, G2 are going to infinity. Now, the problem is that this is not an inner product, so I still can do the game, but I have to be careful because I can take weak limits of this. That's pretty much fine, but then G1 is also moving, and so I could take weak limits of this, but then this product, so weak limit, you cannot send both simultaneously at infinity. You have to do one by one. But you are right, there are proof of multiple mixings playing these type of games. Okay, so it's not that you cannot do it. You just need to be careful. And it's hard, but it is done. I don't know what is the state of the art, but it is. Okay, now let's see the time. Good, we have enough time to do the preparation. So now we will show property T for SLNR guys. Let's move here. Okay, now let me remind you what is property T. So it means the following: I take pi from G unitary representation, continuous unitary representation as before, and we want it not to have almost invariant vectors, or equivalently, we are saying essentially that given K contained in G or S compact and epsilon positive, there exists B norm of B equals to 1 such that norm of pi G of B minus B is less than epsilon, then we say for every G in S, then we say that B is an S epsilon pi almost invariant vector. Okay, so that's what it is. So it's an open condition. So whenever I move the B a little bit, it will keep being almost invariant. I also can do some convex combinations. It's not really very useful, but you can do all this stuff. And then the definition is that G has property T, as always locally compact, second countable house or whatever, which makes G reasonable, if whenever pi has almost invariant vectors for every S and epsilon, then it has an invariant vector. So if for every compact set, which typically you think of it as generating set, you have, and for every epsilon, you have a vector which is almost invariant essentially, norm 1, then it's because you actually had the invariant vector already. So, and it's important to think this in the negative forms in a sense. You can always, as we have said, assume that pi has no invariant vector at all by just restricting to the orthogonal complement of invariant vectors. And then this is telling you that if G has property T, then there are no invariant vector, almost invariant vector, which means that there is S and epsilon and without the V doing the game. So it's really.
By invariant vector, you mean non-zero invariant vector?
Non-zero. Yes, non-zero. There is a non-zero. Absolutely. Okay, so how do we find an invariant vector? Okay, because if we want to show property T, we need to be able to find an invariant vector, and the theorem 2 is one of the best approach to it. So I only need to know invariance by one of these H's. Okay. So as soon as I have some invariance with respect to anyone, I'm done. And even if you put Mautner, if you put Mautner join with this, if the guy were diagonal, it also would do. Okay? We're going to find more than that, but you see how little we need. For this, we need to, so it's the original proof essentially by Kazhdan does the following. So you are assuming you have almost invariant vectors, which means that no matter who is the s and the epsilon, you will get your invariant vector. Then if I restrict my attention to just this SL3R here, 0, 0, 0, 1, 1. Then I will have an almost invariant vector for this guy. And then this almost invariant vector, if I manage to prove property T for SL3R, it will have to be invariant by this whole SL3R, and then in particular for one upper triangular or diagonal or whatever element. And then I apply theorem 2 and tell me that this guy is fully invariant. And then I won. So I only need to prove it for SL3. And that's actually what Kazhdan did. He only proved it for SL3. So let's forget about SLN. Let's just concentrate on SL3. One can do it directly for SLN, but it's really no need to make it more complicated. Now, inside SLN, there is a subgroup, which is also very important. And is this subgroup, which is SL2R, semidirect R2. Now, this group will not have property T, okay? Because it has as a factor SL2R. And property T pass to factors. So, but what I want to get, since SL3 has property T, when I restrict to this action, I have almost invariant vectors. And what I will try to show is that there is an invariant vector invariant by these two entries. Actually, for one, just invariant by one of the entries would be enough, but I will get it at the same time invariant by both entries. And once it is invariant by these two entries, then it has to be invariant by all SL3R by this theorem 2. Okay? So this is what is called relative property T, and that's the main reduction, which again goes back to Kazhdan itself in his original paper, which says that if pi is a unitary representation, has almost invariant vectors, for every epsilon and s, then pi has an R2 invariant vector. And here the R2 here is identified with identity cross R2 over there. So these two entries. Okay, so we just need to prove this theorem. Now, this theorem follows from, well, there are several types of proofs, but I guess still most of them are more or less alike, I would say. The idea is to play a little bit with spectral theory in dynamics. Okay, something that we have done in our ergodic theory classes, I guess. So let me just go back to a little bit of spectral. Actually, let's forget this in dynamics, but it is this. So, and let's just concentrate for a second in this R2. So I restrict pi into U of H. Now, if I have just one operator, unitary operator, here, then the spectral theorem tells me that there is a measure on the circle, okay? And actually, for any pair of vectors VW, there is a measure mu VW on the circle such that u of b dot w is the integral of lambda d mu VW of lambda. And actually, the integral is over the spectrum, so I don't need u to be unitary. If it is normal, even if it is unbounded, but normal is still okay. If it is self-adjoint, you always reduce to self-adjoint anyway. But that's what the spectral theorem says you in this setting. Now, instead of having just one guy, I have a one-parameter group, ut, which is the case r equals to 2, then still is the same. It's actually the very same result. You simply write it a little bit differently. Okay? So you take the generator of the one-parameter group, so D and this is the generator. You analyze the spectrum for this guy, and then you end up with a measure here, and then you do here e to the I t x, and this should be an x, and you have this expression. So it's like the u is the Fourier transform of this with respect to these b and w measures. Good. And actually, the way you do it, you always do it just with itself. And this is bilinear, blah, blah, blah. You use whatever polarization, and you have all the measures. And eventually, you have the what is very useful, the calculus that says that if m from the spectrum, actually I put R because I was thinking, well, in this case it's unitary, so say it's self-adjoint, but if it is unbounded, even if it is self-adjoint, so principally it is in C, doesn't really matter. So if M goes from Z into C, I guess, actually from spectrum into Z is Borel measurable, unbounded, then we can define the operator MUT, which will commute with UT and will make that the definition is actually MUTB dot W is the integral of M of X d mu B W of X. Okay? So it's just one operator, even though the notation, because it depends on the whole parameter group, but it's just one operator. And to recover the u to the t, you just put m equal to e to the I. A very particular situation case of this is when you take m equals to the characteristic function of a Borel measurable set, and in this case, this gives you projections, because this is an algebra isomorphism from this bounded function to the algebra of operators commuting with bounded operators commuting with this one parameter group. And here then p squared equals to p naturally. Okay. So this you do for one u, this you do it for a one parameter group, and the same thing you do for a two parameter group. Okay? And actually, since these are unitary, this guy, as I said, goes from R. If it were normal, then you have to extend, but this is unitary, so you get R. And here is the same theorem, the same calculus, you have measures mu bw such that pi of t, now t is under 2, but still, dot w is the integral of e to the I tx dot product here now d mu v of x. So you have this family of measures, bw. So that's standard spectral theorem. And so one thing, second thing, we have as well the calculus, which tells you that same setting, m now go from R2 into R or into C is bounded. So it's L infinity and Borel. So it's an L infinity functions, but it has to be pointwise because, well, I could speak about the spectral measure, which is a guy that dominates all the guys, but just say it's a function defined everywhere there. So it's bounded and Borel. Then I have this operator m of pi equals to the integral of m of x d mu b w of x, and this is defined. Okay? Good. So far, so good. Okay, no, I don't want to erase this. I don't have too much time, but I already did 90% of what I wanted to do, so I'm almost finished for today. Because I told you, the question is where I'm going to find the invariant vector. The invariant vector will come from here. So I just had this theorem. I have to prove it. And here is the claim. If there exists V such that mu VV has an atom at 0, then there exists V, actually, yeah, may not be the same V, V bar in H, yes, V bar different from 0 such that pi for everything. Okay, so, and it's an if and only if. So atoms for these guys correspond to this. Even more, if V bar were an invariant vector, then this will be delta 0. And the fact that B has an atom at 0, it means that it has some component on the space of invariant vectors, and it is being detected by mu BB. And the proof is really straightforward. So you take your function m as being characteristic at 0. It's a Borel measurable function bounded. It's delta at 0 essentially, but it's a measure. And then we have this m of pi, which is this, which is the projection onto this spectrum part, which is point spectrum. So, oops, have to be projection. And then naturally, if you follow the definition, pi chi 0 of B dot W is equal to the integral, but I'm only integrating at 0. So I'm just getting the value at 0. So, which is 1. So I get that this is mu b dot w of 0. So that's what I get on one hand. The second thing I get is the commutativity. So pi chi 0 times pi of x. Now, what is this? This is the same as m bar of pi, where m bar of z is chi 0 at c times e to the 2 pi I z dot x. Okay, so when I multiply these two operators, this operator is given by this function, this other operator is given by this function, the product of operator is given by this product. But this product is just this guy, because the others are not collaborating. So this function is 0 outside from x equals to, from z equals to 0, and when z equals to 0, this is 1. So that's this, which means that this is the same as this projection. And actually, I want it the other way around. This is the same as this, which means that this projection is a projection into invariant vectors. Okay, done. Because I just need to show that this projection is non-trivial. Then I will get the invariant vector. How do I prove this projection is non-trivial? Well, if this projection were trivial, this product has to be 0. But now, I take my B, I compute this, and this is not 0, because it has an atom at 0. I'm done. Okay, so I just did the computation, but it's what we knew from everywhere. So the spectrum, whenever you have the operator, you use this spectral theorem, the spectral calculus, to prove that the spectrum divides into the absolutely continuous spectrum, the point spectrum, and the singular spectrum. And the point spectrum corresponds to eigen directions. And that's what I just proved, that the point spectrum corresponds to eigen directions. So I cared about 0 because I wanted eigenvalue 1. If you want an eigenvalue different from 1, then you just, instead of looking at an atom at 0, you look at an atom somewhere else. And then you will have the corresponding functional blah, blah, blah. Okay. So that's how we are going to show. So we are going to do it on Wednesday. We're going to take this spectral measure and show it has an invariant vector. And maybe give me 1 second more. And what's the whole point here is I have this SL2R semidirect R2, and I just was concentrating on the action of this. So restrict the representation to this. Now, SL2R acts on R2. So when I multiply matrices here, it comes from SL2R acting on R2 by the standard action of SL2R on R2. Okay? Which means that when I consider this product, this is determined by this measure. Okay? Now, when I determine this guy, where G now is an element of SL2, and I have the complete action. So this is determined by the measure mu pi G of B, pi G of B. Okay, so we're integrating here. But now this guy is the same as put B here and put here pi of G inverse. And now when I conjugate this pi of x, or actually putting together pi G inverse x G applied to B, when I do this conjugancy, this G inverse xg is nothing but G star x. So it's the application of the SL2R matrix G to the x in R2. Okay? Now, this will imply, we will see, is just follow from the calculus, that this is, on the other hand, G star mu BB. And then these two measures coincide. So when I switch from measure by applying pi G, is the same as applying G star. And now we will use this phenomena to show the existence of the invariant vector. And let's stop now. So I just need 5 minutes, but it's better to finish now. Okay, see you on Wednesday. So let's go back. It is, yeah, everything is working. So yeah, we were discussing property T. And let me remind you how we were playing. So we were showing it for SL3R. So we made some argument using one of the theorems we used to prove Howe-Moore, which is invariant by one of these upper triangular matrices implies full invariance. And so using this, essentially, we came up to the reduction that if we prove property T for SL3R, this will imply property T for every SL in R. And actually, we saw that it's enough the following, which is not property T for this group, but is the property that if you have invariant vectors for this guy, then you have actually invariant vector for these R2. So we have this group here. Which is this semidirect product. And then we assume for every k in here, compact, and for every epsilon positive, there exists V in the Hilbert space such that norm of pi G of B minus B is smaller than epsilon for every G in K. So this is having almost invariant vector for almost everything. And we want to show from there that this implies that there exists the bar invariant, not 0. And here, of course, is norm of B equals to 1. Invariant by these matrices. And once I have invariance by these matrices, then we know you have full invariance by the whole SL3R. And actually, if we are thinking of this SL3R or even these matrices as these 3 times 3 guys, and then all ones here, 0, 0, once I have invariance by these guys inside everything, I will have invariance for everybody as well. Actually, I only need invariance by the guy above here. But the way it goes, I need the whole R2 to do the game. So that's how we are supposed to prove property T. And the analysis was to actually first understand this R2 representation. So we restrict pi from R2 into unitary of this Hilbert space, and we have this calculus and that spectral theorem telling us that for every v in H there exists mu, a measure on R2 is a positive measure. Is it positive, or yes, it is a positive measure. So it's a standard measure. So since I'm going to fix the v on R2 such that mu of R2 is norm of b square. So it's the total. Wait a second. Yes, mu of VV is a positive measure. So mu VV, whose norm is that. It is bilinear in VV, meaning that actually I can define mu VW, and this would be a bilinear business. Second thing is that pi of x for x in R2, this is time b dot product v is the integral of e to 2 pi I x dot t d mu vv of t for every x. That's actually what characterizes these measures. 3 is the calculus, which says that if m goes from is Borel measurable and uniformly bounded, and L infinity, well, L infinity sometimes has some connotations, so uniformly bounded, then we have the operator m of pi, a bounded operator of H, such that m of H v dot v is equal to the integral of m of t d mu vv of t for every v. Oops, and this should be pi. So it satisfies this. So it's actually defined by this property, and it also satisfies that. So 3 prime that m pi times pi of x is pi of x times m pi, and also we have that m1 of pi times m2 of pi is equals to m1 times m2 of pi. So in a sense, you take the algebra of operators commuting with pi, and yeah, this is for every x. So the algebra of operators commuting with pi, and this is isomorphic to L infinity on R2. And of course, it will be an L infinity with respect to the spectral measure, which comes to this mu VV guys, that eventually you can make a largest set of full measure for this mu v, which is actually the spectrum, and you have the spectral measure on the spectrum, but we don't need really so much. So it's just standard spectral theorems. And do we need anything else out of it? I guess that if m equals to 1, then m of pi is identity, and if m is this e to the 2 pi I dx, then m of pi is, let's say mx is just pi of x. So actually the first is a consequence of the second plus this property.
There's a question.
Yes. Good. Okay, 1 second. Okay. Series having 1 and 2, of course. A very good question. I think yes. I think once you have this definition plus this other one, 3 prime should just follow from this property. If you have 3 prime, then you can recover this, and if you have this, you can recover that. Yeah, I agree. I agree. Yes, yes.
I think if you use the square.
Yeah, exactly. Good, very good. Okay, but in any event, out of all of these, what you just want is the corollary that says that if there exists a V such that mu sub VV has an atom at, actually, let me state the more general corollary, and then the second corollary is the one that goes right to our point. An atom at T naught in R2, then we take M equals to the characteristic of this T naught. We define P sub T naught equals to M of pi, and we obtain that P square, so it is a projection, and it is non-trivial because PT naught at B dot B is equal to mu VV at T naught by definition, which typically would be 0, but if we have an atom, then this is not 0, which means that P T naught is a non-trivial projection, and we have that pi of x times PT naught of B. This is equal to, by using the previous thing, as m of e to the 2 pi I of this function, oops, not of this function, okay, yeah, x was a good thing, x dot T naught times T naught. Well, actually, I don't need to put the variable. So it's this constant times this, and this is just a number, so this is e to the 2 pi I x dot T naught times P T naught of B. And actually, this I put for B, but this is true for W, for every W. Okay, for every W. And which means that this PT naught is nothing but the projection, actually orthogonal. We also have the fact about the conjugate, so it's an orthogonal projection onto this eigenspace over here. Okay? Now the case that we want, so i.e. PT naught goes from H into this ET naught, where ET naught is equal to all the V's such that pi x of B is e to the 2 pi I. I don't know where, it's a matter of notation. Yeah, I put the 2 pi I. 2 pi I x dot T naught times V for every x. So it's this projection, and what we get is the case of T naught equals to 0. Okay, so taking T naught equals to 0, I have that. So corollary 2. So taking T naught equals to 0, we have that if 0 is an atom of mu VV, then these invariant vectors of pi restricted to R2 is not trivial. So we have some non-trivial invariant vector, which is what we are looking for. So then I need to find the V, some V, so that mu VV has an atom at 0. And then actually it will be, you see, for the invariant vector, it's fully atomic at 0. Okay? So, okay, so how we find the invariant vector, and this is just geometry. So the second property, and again, this follows from the calculus plus doing some computation, of course, and some continuity and approximations. We have that so proposition mu sub pi g v of B, where G here belongs to SL to R, so it's of the form so this type of G. This is the same as G star, where I make this G act on R2, and I will explain in a second better what is this action times mu VV. Okay, so that's the proposition. So let's discuss for a second this action. So we know that this the standard action of SL to R in R2, but whenever we have this semidirect product, which means, and here is really something that I never able to do it correct, but let me try anyway to try to. So the fact that you write the semidirect product that way means that this guy is a normal subgroup here. And I think I wrote it correctly. R2 is normal here. Now the fact that R2 is normal here means in particular that when I do G R2 G inverse, this is equal here. So whenever I have the semidirect product, I have this factor acting on the other factor by conjugation. Now you do the computation, you conjugate, and you realize that this action here that I'm writing here, which is the one by conjugation, is exactly the same as the standard action of G in R2 by multiplication. And this is just a matter of product of matrices. When you do the complete product of matrices, you take this matrix, you multiply by this matrix, and then by the inverse of that matrix. And here you get A, here you get A times V, or V is V1, V2, here you get 0, 1. This is the product of these two guys, and when I go and multiply by the inverse of this, I just killing this A and not modifying this. I'm getting identity AV01. And that's how I'm really acting. So that's what explains one thing, and the other thing is now is a matter of how the calculus applies, because this measure is actually determined by this product. Okay, now this is the same as pi G inverse times pi x times pi G V dot V, because it's a unitary representation, so you transpose is equals to the inverse, and this is the same as pi G inverse x G V dot V. And now this new vector is the G star x, is G times x, but now in this action version of it. And then you go and look at the calculus, essentially. And this will tell you that this is the same as playing this game here. So when you write down the integral, here it is. Maybe I go over there and erase. So I just erase it, but when I do and here is really comes something that we didn't discuss, but we should have. So I'm using an abuse of notation when I write this, because I'm using x to understand this matrix on one hand when I write pi of x, and I'm using x as well as x1, x2 when I write this dot product. Okay, so then when I'm writing g minus 1 xg, and the same with the g, I'm writing g for the matrix g 0, 0, 0, 0, 1, and for the g in SL2R. Okay, and I guess the inverses here go that way, so in any event, when I do all these identifications, what I get here is that I'm having g minus 1x dot t, and then this goes to the other side at x dot g minus 1 transpose times t, and then this goes all the way to here as the integral of e to pi I x dot t d g minus 1 transpose star mu bb of t. This t is for transpose. Okay, and then I put this star here, and well, it's not actually, maybe I should be careful. And it's actually this automorphism of SL2R, which is the inverse transpose guy, and this is actually the guy acting. And that's the proof. Okay, so that's first observation. Second observation, so maybe observation 0, so since we are still trying to get an invariant vector, let's try to see what happens if we knew we have the invariant vector. Okay, so if pi g of b were equal to b, this implies that this measure mu vv is invariant by this action. Okay, but this is the action on R2. And here is 0. So this action, if I take G so that G minus 1 transpose is this matrix, for instance, then you can see that this line, when I apply this matrix, comes into this line. And then when I take this cone without the 0, let's just take the forward cone if you want, and I start applying this matrix, this guy goes to this guy, that goes to this guy, and so on, and they are all disjoint. So if the measure is invariant, then I get that all these guys will have the same measure, and they are disjoint, which means that I can not sum infinitely many of them unless they have 0 measure. So this way I show that the upper plane has 0 measure, the down part also has 0 measure, and then I can just do a rotation. And by rotating, I just prove that the complement of 0 has 0 measure. And then I just got the 0. Okay? So the measure has to be delta 0. If I had full invariance, now I will play the same game without full invariance and get an atom at 0. And that's all I need. So, but for this, I need the second statement, which is that the total variation of this measure minus this measure, so this is total variation, which amount to decompose it into positive and negative part, and then you take the sum of the positive plus the negative part of this measure, but you do some not too complicated bilinearity here, and you can bound it by the norm of pi gb minus b, by some bilinearity, essentially. So which means that the total variation of this I control by this guy. And now I will apply the trick we were discussing. Okay? So take the compact set I'm going to take is, I may be wrong, but let me just eventually fix it completely towards the end, but in principle is this guy, and then rotation by I guess pi over 8 should do, or pi over 4, pi over 8. Actually, okay, SO, okay, is compact. So and I guess, yeah, with this guy and SO, essentially I should be able to do it. So I have this, the compact, and I take epsilon very small. We will check how small I want it. So I will need 35 times epsilon to be smaller than 1, something like that. And I can assume then take V such that pi g of b dot, and norm of v equals to 1, such that this is less than epsilon for every g in k. Okay, then the fact that norm of v equals to 1 tells me that the spectral measure is a probability measure. And now comes the picture, which is repeating the picture above. On one hand, I have G star or G minus 1 transpose. And yeah, maybe let me put minus 1 transpose. So it's this guy and star mu VV minus mu VV, the total variation is less than epsilon for all the G's before, so in particular for the 1, 1, 0, 1, and for the whole SO2R. I have this property. Now I do the same game. I take this guy. So this line is the image of this line. And okay, now I have to be epsilon careful. I think I'm forgetting another guy. Probably I want both actually. This, so then I have also this guy. Okay, so when I apply once this guy, so this has some measure. Then I apply it again, and this guy goes to here, and they are disjoint. Okay. Then what should I do? Oh boy, it was so clear today in the morning. I want to show that actually this guy has small measure related with this epsilon. And the way I'm supposed to do it is by first showing I have some cone like this of small measure and then rotating it to cover everything some finitely many times. And the point is that it's the same epsilon, so I can take epsilon very small as soon as the operations I'm doing here are uniformly finite, independent of epsilon, then I can cover all R2 by a set of measures smaller than some multiple of epsilon, and then I just make this multiple of epsilon smaller than 1 by shrinking epsilon, and it means that 0 need to have positive measure. So that's what I'm trying to do. So let's see if we can do it. So, okay. So I take, let's see. So if I take this guy maps into here and then into here by applying these 2 times. Then I have that the measure of this is up to an epsilon, the same as the measure of this. So once I know this, it means that means what? Now I have to argue that the measure of this is small. How do I do it? The second, non-trivial trick. Okay, when I apply this other guy, this comes into here. Okay, now we are talking. Yes, okay. Oops. So This is the dynamics of 1, 1, 0, 1. Here is the dynamics of the 1, 1, 0, 1. It pretty much does the same, but it brings this guy into here. Or maybe I need to put the -1 here to do this, because I'm the negative side. Okay, so that's the dynamics of this. So what I conclude with this is that I take this quadrant here and this quadrant here, decompose into this part and this part. This part is mapped here and this part is mapped down here. And then what? Why this is? How do I kill the measure of this? Maybe I need to take even smaller guys. Wait a sec. Okay, I need to show that this measure is okay. Okay, now we are talking. Okay, here it goes. Sorry, it took forever, but eventually it is conversion. Okay, so okay, take a k, maybe k is not a good number, and very large. Okay, and then we put all these powers and maybe this as well, and okay, this is a k sub n. N will be fixed at some point, and epsilon will be shrunk a lot. Okay. Now I take this guy, and I will show that this guy has very small measure for this choice of v and for a very large n. And the reason for this is I can take this guy, I move it into this by one iterate, and the measure of this, the difference with the measure of this is at most epsilon. Then I do it again, and the measure of this, different with the previous one, is at most epsilon. And then I do it for some amount of time, n times to the future. I could do n time for the past as well, but let's just do n time for the future. Okay? Then, if I do it n time for the future, I have that the total measure of this guy, this is like the measure of this guy times n plus, and then I have the accumulations of the epsilons. So each guy was up to epsilon the previous one. So how many epsilon did I put? N epsilons or n squared epsilons? So the measure of this is this plus epsilon. The measure of this is this plus epsilon, which is this plus 2 epsilon. So I get an n squared epsilon here. Okay? So that's the measure of this guy. Up to some constant. Okay, so I can show that then the measure of this guy is at most this. Now this is less than 1, because the total measure is less than 1. And so I get that the total measure of this 45-degree angle is smaller than 1 minus n squared epsilon divided by n. Okay? So far, so good. Now, I rotate 8 times this guy, and I cover everything, so the complement of 0. So I get that mu of R2 minus 0 is smaller than essentially 8 plus 8 epsilons. It just doesn't amount to much, so it's C times 1 minus plus C prime, the same C, epsilon. Okay? And I get that for every measure which has, for every element in Kn, this smaller than epsilon, I show this. Okay, now I can pick epsilon and n to my will. So I take n very large, I take epsilon equals to 1 over n to the 100, and then this get killed, so I can forget about this. I can assume this is 1/2. This is 1 over n to the huge. This is just n. This guy is smaller than 1. And so 0 is an atom. Okay, I'm sure there is a more optimal way of doing than what I did, but that's pretty much the game. Okay, so you could do it by yourself. What is the final game? So you just don't need full invariance to do this argument. You need just epsilon invariance and make it the right choices of guys. Okay, so this shows.
So you assumed almost invariance at the beginning, and
Yeah, well, you assume you have this property, which comes from the almost invariant vector up here.
almost invariant for K
And exactly, so for every compact and for every epsilon, you will have such a vector. So then you are able to make your choice of Kn. Of course, you change the choice, the measure will change. So your argument shouldn't be about the measure, but about these properties of the measure, which is, so this is a very geometric property. So what I needed is enough amount of guys to cover this part of the space. And then the fact that I do it 4 more times, 5 more times, 6 more times, and I cover everything. Okay, so this bound here, I got for every measure, so for every mu such that G star mu or G minus 1 transpose star mu minus mu total variation is less than epsilon mu probability. For any mu doing that, and this happening for every G in this Kn union SO. So for all such guys, I have this property. And then I claim that, well, if I make the right choice of n and epsilon, then this is smaller than 1. And then the corollary is that for any measure satisfying this, for the right choice of n and epsilon, has an atom at 0. Okay? And having an atom at 0 is everything. So you won. Yeah, sorry, it was a little bit messy. But
And how did we know that mu is a probability measure? Does it come from the spectral theory?
no, yes, spectral theory tells you that the mu of R2 is the norm of the vector square.
Right. Okay.
And you choose a unit vector. So. See, actually, this is a very important game. So it's the better you play it, the better results you get. And when it comes to getting improved version of Kazhdan or making some use applications and everything, people really are very smart on what are the right choices of G's and how to play this game in the most optimal situation. So, which is taking advantage of the epsilon and the compact set the most you can. So, okay, so, but at least we finished property T. So this gives property T, and then what is left to prove for our proof of normal subgroup theorem, I will just, since I already have no minutes, so I will just leave it as an exercise, but I will tell you how to do it. And so the proposition says that if G has property T and gamma is a lattice, then gamma has property T. Okay, and the proof is, we essentially already played with this, simply in a different, more geometric context, but this induced representation. So that's the basis of the proof, which means you start with pi from gamma, some unity representation of gamma, and then you induce a representation of G into another Hilbert space, which actually depends on pi of gamma, and it's pretty much the same thing we did for the action of gamma on X, and we did a suspension, and from there we get an action of G. And here you just, in a sense, this is the suspension of this representation. So, so you look at functions from G to H. Yeah, that's it. So I don't think I need to assume much more about them. Probably, since I want Hilbert, I think I want these functions to belong to L2. Do I want them to belong to L2? Certainly, I want them measurable. Maybe I want them to belong to L2. We will see in a second. Or it will be left as an exercise. Yeah, I certainly want something because well, that's not yet the space, so I will quotient this by a relation. So this is like doing G times X in our previous situation, but now I want to identify functions according to the representation. So I want that U of G. So I have the left action of gamma on here, and I have the action of gamma on H. So, and I want to identify these two guys. So I say that U1 is equivalent to U2 if there exists gamma in gamma such that U of G gamma is pi gamma of U2 of G for every G. Okay, so that's the natural relation you put there. And yeah, I certainly need to make this into a Hilbert space, so I really need some integrability. So I assume that the integral of norm of u of g, so this is the Hilbert norm here, dg, this is finite, and this is L2 of these functions essentially. So this is again naturally Hilbert space. This is a relation which actually corresponds to a subspace asking pi, or whatever it needs to ask. And so I can just take the quotient, which again will be still a Hilbert space. And this is h gamma pi. And then I have my representation, which is just right multiplication by g. Okay, so pi g of u is u of at x is u of gx. Essentially. Okay. So yeah, if you want, you have this. Yeah, maybe that's better. You have this representation on this space, and this representation goes to the quotient because it satisfies the right property.
So the thing that we call h gamma pi is this quotient space.
Exactly. So h gamma pi is this. Is this Hilbert space quotient by this relation, which is again a Hilbert space with the natural quotient guy. So this relation is actually coming from a closed subspace, essentially. And once you have this new representation, it will be as continuous as before. So the importance for continuity is the fact that the standard representation by multiplication in G is a continuous, because gamma is essentially discrete. The fact that life is nice is because gamma is a lattice, so G mod gamma has finite volume. This is very important to be able to restrict things to fundamental domains and make the argument. And especially important when you try to show that if you have an almost invariant vector here, then it is also almost invariant here. Okay? Actually, well, it's not an also. It means that if you pick a compact set here and an epsilon, yeah, maybe I should be more careful. Pick k and epsilon. You take k and epsilon, k a compact subset of gamma, epsilon any number, and assume you start with an almost invariant vector for this guy. Then you want to define an almost invariant vector here for some compact set and the corresponding epsilon. Okay? And then, yeah.
You really need the lattice assumption. Like
Yes.
If we're just a discrete subgroup, I don't think this would work.
It's false. If it is just a discrete subgroup, it's false. So you can define this induced guy, but it's very weak to really capture everything. So then you really need the lattice. Essentially, the lattice comes from being able to translate information about almost invariant vectors here to almost invariant vectors here. And yeah, there is some work. It's not 100% trivial, but it's quite routine and fun. So, and then
You really need this, like a very nice fundamental domain here.
yeah, finite measure essentially, because you need to be able to upgrade the epsilon there to an epsilon here and vice versa. And for this, you need the finiteness of the fundamental domain. Actually, if the fundamental domain were compact, I think it's a little bit simpler even. But it's not so important. Because I think when it is not compact, you really have to play a little bit with taking a compact set whose complement has very small measure. So then what you are losing outside from this compact set is very small, and it will not affect this integral and everything. So yeah, and the norm here you put here is essentially the inherited norm, but it's essentially integrating only on the fundamental domain of this guy. So that's how you write down the norm of this. So you take a representative and you only integrate on a fundamental domain, and this is well defined because this is unitary, so it will not affect the norm when you jump from one fundamental domain to the other fundamental domain. That's pretty much what that this is a good space. Okay, so I guess that's it. We are more than enough. Okay, good. Yes. Okay, so yes, it's time. Any more questions or anything? Great. Okay, then okay, so see you on Friday then. Thanks. Bye. Okay, so let's start. So let's go back to the proof of our normal subgroup theorem. So we established the ergodicity we were willing to establish. So let's see where we stand. So we started with gamma acting on x, actually gamma over n. N was a normal subgroup of gamma. Gamma was a lattice in G. G is ln R. What else? P in this situation is this A times N. And this is this guy. Now from there we increase into this gamma acting on x. From there we created a map, equivariant, doing this game. We call this guy Z, and we had our factors theorem. All by Margulis, of course. That's it. Under this situation, we put always lambda there. Z no. Gamma acting here, gamma acting here. Then we have this following picture. Q mod G, lambda, and this is an isomorphism. And this is the natural projection. And we saw how to deduce the normal subgroup theorem from this isomorphism. So now we have to prove that such isomorphism exists whenever we have such a factor. Actually, I don't remember how we called it at that point, but let's call it pi and this h. It really doesn't matter. Now, using this factor map, we built our fibered space which has a G action, which project into here is a G action. This factor in the first coordinate gives you this factor. Here we put lambda, and the measure mu over there give rise to a measure mu tilde. Maybe let's put this separate, because we have mu tilde projecting to lambda, and this is P invariant. Now this P invariant measure is Q invariant for this Q. Which is a closed set, closed group containing P. And we want to show essentially that this is best possible. And the way we state this being best possible is like the following. Mu P G and we define it to a constant for mu tilde almost every P. So I have the G orbits in this space. I condition my measure to these G orbits, and it ends up exactly the Q measures there. So this is actually Haar, again up to a multiple on Q. And actually we don't prove that this is equal to that, but that this is equal to Haar. And that's actually what is useful. So once we have this lemma, then it will be reasonably simple to show that this map is an isomorphism. Actually, it's injective. So this map is naturally defined because the definition of mu tilde will tell us that this map is constant on the corresponding Q, and then I can just move there. So this is all from lemma. And the reason for that, maybe let me emphasize that. So this function is called pi, well, actually it's h. Is essentially, so here is essentially the G orbit of any point in H minus 1 of C, quotient by the Q orbit of blah blah blah. Okay, and now by having this equality, the G orbit divided by the Q orbit is just 1 point, because this measure is the same as this measure, and hence this is just 1 point, and that's what we need to prove. Okay. Now we need to prove the lemma. And for this we have a couple of integrands. So take ij, I different from j, both between 1 and n, and actually I want them to be lower triangular. So this is I and j, and if I want it to be down here, I want the other one. Okay, I larger than j. Then we define hij s as being s here, 0, ij position, so this one parameter group. And the lemma says that mu tilde ij p is Haar measure. So either for every okay, ij are fixed. So either this is Haar measure and mu tilde is or mu tilde p almost every point, and mu tilde almost every point p, and HIJS star mu tilde is equal to mu tilde for every s, meaning that this guy belongs to Q, or mu tilde IJP is delta at P, and again this is like that, this also, but this is less harmful, for mu almost every P. So I fix ij and I get this dichotomy. So either I get the guy is invariant or the conditional measure is atomic. Now, if you go to this picture and see what we are willing to prove, I hope I can convince you that this is really a good step towards it. Because I have here the G orbit, here I have the Q orbit, and then here I have an HAGS orbit. And now I want to claim that if it is like in the picture that Hij is not inside Q, then the measure along this line has to be atomic. And the atom is essentially the intersection with Q. And that's what the guy is telling us. So in the first case, we get that the guy is inside Q. Then not much is to be said. Naturally, I will have Haar. And if not, I just get one atom. Okay. So the proof of this lemma is very easy once we have all that we have developed. Let's move over there now. So we have that this guy, this flow, not this guy. Very sorry. So we take this guy, E is 1, 1, 1, e to the t, e to the minus t, 1, 1, 1. There's also 1, 1, 1 here. This is in the I position, and this is in the J position. And the rest is 0. And what is important is the fact that if I do AT, H, IJS, A minus T, I get the very same guy. If I did things correctly. If not, I have to work it out. Maybe not. Actually, I want exactly the opposite. Yeah, I'm sorry. Let me just put the more general situation. Ti e to the tj e to the tn, and I want ti equals to tj. Yeah, it's exactly the opposite of what I wrote. Now this is true. So I act isometrically. Now I look at the action of this AT on x gamma. Remember, this is G mod G times x mod gamma. It preserves the measure mu tilde because this AT is in P. And it is isomorphic because on the P I have this isomorphism. Now, Howe-Moore tells me that this is ergodic, and hence this is ergodic. Okay, now that you have ergodicity, now I apply what we did for matrix A and B. So we have this space, W ij of P. We have the parameterizations. I will not write down everything, but it's just follow from here. So HIS, well, I should put a P somewhere. Let's put it here. Into X gamma, which is HIGP of S is HIGS of P. So these are the parameterizations. In these parameters, the dynamics is actually isometric or multiplication by whatever, but by this choice of T, it is fully isometric. And then I can run the scheme. And running the scheme tells me exactly that. So it tells me that the measure mu tilde IGP is either an atom at P or Haar on this one parameter group. Okay? It's really the same proof. So this proves the lemma. Now I need 2 more steps and I finished. And we finish with the normal subgroup theorem. So today will be one. On Monday I will do the other. But let me draw the picture. So I have G here. I'm drawing it three-dimensional, even though in the simplest situation it's essentially eight-dimensional. But so this is the, okay, let me put P, which I knew invariance because I started from there. Yeah, maybe I need more. So let me just do Q after I know this is Q. Now I take this Hij, Hi prime, J prime. So two different directions. Now I know that any direction where this guy were Lebesgue has to be inside Q. So which means that conditional along here is delta, and conditionals along here is delta. Now imagine for a second that that was all. So let me even go to the concrete example where this picture makes a lot of sense. So let Q then be imagine Q is this guy, and then I have these two entries, H21 and H31. And I know it's delta along this guy and delta along this guy. And then I have this plane, this subgroup corresponding to these two guys. So this is a subgroup, and I can consider conditional along these guys. And I want to claim that these conditionals are delta as well. So that the fact that I have delta here and delta here implies I have delta along these planes. So this is a non-trivial statement. So it's some joint integrability of the deltas. So it's the fact that this measure is roughly the product of the mu in the 2-1 times mu in the 2-3. Because once I know enough about this product structure, this being delta, product of delta give me delta. And actually this is true. I don't need to know they are delta. Whatever I have there and whatever I have here, I will have this product structure. A little bit more will be true. So once I manage to do this, I need to handle some other guys. So guys that do not commute, because these two entries commute, and that way they jointly generate n. When they don't commute, we have to do something. It's more or less the same, but still. And then I need to use the last step to claim that because this is delta, the conditional measure is inside Q. There is no one else. If there were another one else, there will be another Q orbit. I will detect another point here. But this again has to do with some other product structure of the measure I will have to discuss. Now, it's important to understand that Lebesgue measure is a very special measure in all the world, not only in this homogeneous situation. So, what is so special about Lebesgue? Let me try to convince you in this picture. So imagine you have this foliation. This is foliation by vertical lines. And you have the measure on this square. And you know that the conditional measures along each of these lines are Lebesgue, are exactly Lebesgue. Or absolutely continue for that matter, but let's say just Lebesgue. Then you will have that your measure is the product of dy times some measure in the base. If I only have absolute continuity, it will be equivalent, but for that matter, it's no difference. Okay. So, and this I know because it's Lebesgue, or again, absolute continuity with respect to Lebesgue. If instead of that, I give you the information that the measure is atomic on each fiber, then the only thing you can say is that it is a graph over a measure. But then you can say nothing about this graph. Typically, it will not be an horizontal graph. Okay. So that's what is so special about Lebesgue. So when we come back to our picture, so this is the G space, here is the Q orbit. I know that along Q orbits is Lebesgue, which means I can really project and know that my measure on this G space is the product of Lebesgue here and something in this space. And since it is a product, what is happening in this plane and this plane is pretty much the same. It's the same measure modulo the identification of these two planes. So which means that if I understand the conditional here, I understand the conditional here. If I know it is delta, then the measure is just supported on a Q orbit. Okay, we are going to go through that more slowly when we say the lemmas. Okay. So let's go to the next statement. Let me see if I remember how it goes. Okay, now I take an ij. And I take another guy, I prime, j prime. Now we take A, t, which is e to the t1, e to the tn, such that 1, ti equals to tj. So this guy is isometrically there. And the second is ti prime minus tj prime is negative. So in the corresponding I prime j prime, I act contractively or expanding, and then you take the inverse. Okay. Okay, I will do it in 2 steps. So assume for a second that the bracket between these two guys his identity so that they commute. This can be explicitly computed, so this implies that J is different from I prime. That's pretty much what it means. Then the following holds. Exists R, mu tilde of R equals to 1, so set of full measure, such that if P is in R and Q is in W I prime G prime of P, so remember that this means Q is H S I prime G prime of P for some S, and I want also to belong to R. And here comes the guy, mu bar ij p. The notation was otherwise. P downstairs, ij upstairs is equal to mu bar q ij. So these two measures are the same. So remember what is mu bar? So I have here wij. I have my parametrization of wij. I have the conditional measure happening here on the wij, and I pull it back, and it's the measure on the real lines, where you bring P to 0. I will write the proof, and I will try to convince that this is actually not needed in the proof, and so we will have the result without this assumption. But in the picture, it will be better to keep this assumption, because I will draw a picture, then I will rewrite it, and in the rewriting, the picture will be lost. And to draw a picture, I need this assumption, but for the argument, I don't need it. So here is the picture. Here is the ij direction. Maybe here is the I prime, J prime. Wait a second. Yeah. And here is the ij direction. Now, if I assume the guys commute, these two guys forms a joint guy. And then I have P here, and I have Q here. So I have here wij of P, and here is wij of Q. And I have the conditional measure mu tilde for P, measure mu tilde ij for Q. Now I apply A to the T. And remember, I have ergodicity and whatever you want. I don't really need ergodicity here, but anyway. Now, the AT contract this direction, but it's isometric in this guy. So when I go to the future, I take a subsequence, Pn, so Atn P will go to P infinity. Atn of Q also will go to the same P infinity because they go together. Now the left-hand side, since I'm having isometric here, will go to some measure mu tilde ij. Of course, to this I need to go to continuity of this map, mu tilde. I have to do the argument. The argument will be this is a measurable function, then this is continuous on a losing set, then I want these iterates to belong to this losing set of continuity. Same with the Q. Then I need to do this argument because I need them simultaneously by the same TNs to belong to these sets. That's fine. And once I have this, I'm essentially done because the left picture goes to this guy. The right picture also goes to the same guy. Now this horizontal identification is nothing but going to infinity from this guy and coming from infinity through this guy. Now this means that when I take this measure, I apply holonomy here, it gave me that measure there. Okay, that's what we are going to prove essentially. Now we need to go to the mu bar. When we go to the mu bar, the point is the way the identification go from here to here and go from here to here, I have that this arrow from here to here is the same as identifying here, and move here. Okay? And that's why the mu bars measure coincide. And actually, on the day of the day, I don't care about these 4 guys. I can just do the argument without this picture and get that the mu bars match. That's all what I want. So let's write down this picture now that we proved, now we know the picture. Good. For once in my life, I think I'm good in time. So we have these maps, mu bar sub dot and j from set of full measure into radon measures of R. So let epsilon be positive, k k containing R mu tilde of k, such that this measure mu bar restricted to k continuous. Okay, that's losing set. So every measurable function is continuous on a set of large measure. What do we know about this guy? We know that AT star of mu ij of p is the same up to a number to mu bar ij of AT of p for everything. And p in R, AT of p in R. And again, I'm using here, because you know that I have to do something, that the assumption on AT is that Ti equals to Tj, so I'm being isometric on this direction. If not, I will have some multiplication by some lambda acting on the real line. But the action is trivial now. Now claim there exists Tn going to infinity such that this distance goes to 0. And Atn of P belongs to K for every n. Actually, for this I only need, I may need less, but I just need less, this being larger than 1/2. Let's postpone the proof of the claim and see how it is finished. So assume claim is true. Second. Now, since Ti equals to Tj, At star mu bar Ij of P equals to mu bar Ij of P. Okay, let me just be careful on that. So the question is, what is this At moving from R to R? And this is just identity, because this comes from Wij of P, At, Wij, of ATP. Here I'm doing the Hij at P, Hip at At of P. And this map here is identity. Identification, identity between R and R. So this tells me that At is doing nothing on this R, so this measure is this measure. Yes, I have that F of P equals to At star mu bar Ijp, which is the same as mu bar At of P. Now assume, by taking a subsequence, Itn of P goes to infinity, and then I get that mu bar Ij Itn of P will go to this place by taking the subsequent and using the losing set. And hence, mu bar Ij, actually not hence, but also, Atn of Q will go to the same limit, again up to a multiple. But I have the qualities always. So mu bar Ij of Q is always equivalent to mu bar ij atn of q. So this implies that a mu bar ij of p is equivalent to mu bar ij of q. That's what we want. And we won. Okay, so let me finish for today by proving the claim. There are two proofs. Proof 1 is easy. It says AT times AT is ergodic. And this is because AT is weak mixing, actually it's mixing. So which means that AT times AT is mixing. And since the provost is ergodic, I certainly have iterates that visit k for the product, or k times k for the product. And I'm done. I will leave the second proof for Monday. Okay, that's it for today. Thank you all. See you on Monday.